Hello everybody, welcome into another lesson. So today's lesson we shift more into the logic unit, and then in this unit we're actually going to start doing our first proofs, which actually the next lesson we will start doing our very first proofs. But today we're going to talk about what's called conditional statements. Then we'll also talk about their converses, then we'll talk about biconditional statements. So here we have the original statement. It's called a conditional statement. That's the original. It goes something like if P then Q. So there are a lot of if then statements. Those are called conditional statements. So the if part, the if P part, is called the hypothesis. The then Q part is the conclusion. So if something, that's the hypothesis. Then whatever it is, that's your conclusion, okay? That's called your conditional statement. Now, to get the converse, to get the converse of that, all you're going to do is switch the hypothesis and conclusion around. So the converse of the original statement is going to be something like if Q, then P. That's the general format. So basically we're going to have an original statement, determine if it's true, then we're going to see if the converse of the statement's true. And then we'll talk about biconditionals in a few minutes. So let's get started with some examples here. Okay, we got the original statement here. Let's start with the original statement. This is going to read, if x equals -6, then the absolute value of x equals 6. Okay, so we have here the hypothesis that if x equals -6, then the conclusion is that absolute value of x equals 6. Is this a true or false statement? Well, that would be true. If x equals -6, the absolute value of -6 is 6. So the original is absolutely true. We know that's true. Now, what about the converse of the original statement? Let's do the converse of the statement. The converse of the statement would be if the absolute value of x equals 6, then x equals -6. Okay, so if the absolute value of x equals 6, then x equals -6. That's its converse. Well, we know from absolute value problems, when they're equal, you have two solutions. This is only one solution, x equaling -6. X could also equal +6. So it's missing a solution. This is only partly true, which therefore makes a statement false. If it's only partially true, you have a false statement, because it may not equal -6, it could equal +6 also. So there's some examples there of, and I got more, of an original statement and its converse. Alright, so what would be the next one? If x squared equals 4, then x equals -2. So this is the original statement. If x squared equals 4, that's the hypothesis. the conclusion is that x equals -2. Again, this is only partially true. X could equal +2 also, right? Since it's only partially true, we have a false statement. Now, if it would have said plus or -2 for the conclusion, then we would have had a true statement. Now, how about the converse? The converse states that if x equals -2, then x squared equals 4. So let's see. If x equals -2, then x squared equals 4. Well, that's true. If you put in -2 to the second power, you'll get +4. So we know that's a true statement. So the converse is true while the original is false. All right. Next one. If b is greater than 4, then 5b is greater than 20. So here's the original statement. If b is greater than 4, then 5b is greater than 20. Well, that would absolutely be true. That would totally be a true statement. Okay? So, if b is greater than 4, then 5b is greater than 20. That's true. Now, what about its converse? If 5b is greater than 20, then b is greater than 4. Alright, so if 5b is greater than 20, then b is greater than 4. Well, solving this inequality, we know that's also true. This is also a true statement. So, here's the neat thing now. Whenever you have a statement, the original statement and its converse, if they're both true, if they both have to be true, the original and the converse, if they're both true, you can form what's called a biconditional sentence out of them. And that's only if both the original and converse are true. So we are going to form a biconditional sentence. So what does a biconditional sentence do? The biconditional is going to take the hypothesis of the original. It's going to say b is greater than 4 if and only if 5b is greater than 20. So the biconditional starts with the hypothesis without the if. It'll say b is greater than 4 if and only if 5b is greater than 20. That's what's called a biconditional statement, when it has if and only if. And there is a way in geometry we abbreviate if and only if. We abbreviate it IFF. IFF stands for if and only if. So that's actually good to know for when we're doing proofs. Use IFF for if and only if. So, yes, if you got, again, both the original and the converse of the statement both being true, then you can form what's called a biconditional statement using if and only if. Okay, what's the next one? If the measure of angle T equals 40, then angle T is not obtuse. Okay, so the original statement is that if the measure of angle T equals 40, then angle T is not obtuse. Well, that would be a true statement. Angle T would actually be an acute angle, so it's definitely not obtuse. So the original is actually a true statement. Now, how about the converse of this statement? It would read if the measure, no, it would, not the measure, if angle T is not obtuse, then the measure of angle T equals 40. Alright, so if angle T is not obtuse, then the measure of angle T equals 40 degrees. That's the converse. Well, right away we should see this as a false statement. We can't guarantee it's 40 degrees. I mean, it very well could be. But if it's not an obtuse angle, it could be a straight angle, having 180 degrees. It could be a right angle, being 90 degrees. Or heck, let's just look at all the acute angles. It could equal 30, it could equal 50, could equal 89, could equal 1 degree. So this is a false statement. The converse is false, the original is true, therefore we have no biconditional. We can't form a biconditional out of this. So these really get you to think logically about stuff. Alright, let's see. If Pam lives in Chicago, then she lives in Illinois. So this original statement is going to be, if Pam lives in Chicago, then she lives in Illinois. Well, that's true. Chicago's in Illinois, so this is absolutely a true statement. She lives in Chicago. She does, in fact, live in Illinois. Now let's take the converse of that. The converse would state, if Pam lives in Illinois, then she lives in Chicago. So the converse statement would state that if Pam lives in Illinois, then she lives in Chicago. Well, she very well could live in Chicago, but there's Peoria, there's Springfield, there's Joliet, there's Urbana, there's so many other cities in Illinois that we don't actually know which city she lives in. So this would be a false statement. We can't guarantee that she lives in Chicago, so this statement is actually false for the converse. So there's that original and converse. So yes, you can apply these statements to everyday life too, not just math. You can apply them to every single day life. All right. Let's see. If angle A is congruent to angle B, then the measure of angle A equals the measure of angle B. Alright, so here's the original statement. If angle A is congruent to angle B, then the measure of angle A equals the measure of angle B. Well, that's true. Congruent and equal, they're interchangeable. That would be true. So the original statement is true. Now what about the converse? If the measure of angle A equals the measure of angle B, then angle A is congruent to angle B. Alright, so the converse statement is if the measure of angle A equals the measure of angle B, then angle A is congruent to angle B. Well, that's true. Yes, angles equal or congruent, they mean the same thing. So the converse statement is also true. So since both the original and the converse are true, we can form yet another biconditional. So let's write the biconditional statement of this. Alright, so the biconditional statement is going to read angle A is congruent to angle B, and I'm going to abbreviate if and only if with two F's, if and only if the measure of angle A equals the measure of angle B. Okay, so the biconditional reads angle A is congruent to angle B if and only if the measure of angle A equals the measure of angle B. So that would be the biconditional of this statement, since both the original and the converse are true. Okay, next problem here. I have four more. I got four more. So if A is greater than 3, then A squared is greater than 9. Alright, so here's the original statement. If A is greater than 3, then A squared is greater than 9. That would be true. That's absolutely true. Now let's deal with the converse. So if A squared is greater than 9, then A is greater than 3. Alright, so the converse is that if A squared is greater than 9, then A is greater than 3. That's only partially true. If we do this inequality, A squared being greater than 9, we also can tell that A would be less than negative 3. So it's leaving out the fact that A is less than negative 3. So this is a false statement, because this is basically trying to say that it's only A greater than 3, when in reality you also have A less than negative 3. So the converse of the statement is actually false. Alright, 3 more. We got 3 more. If x equals 1, then x squared equals x. Okay. So the original statement is that if x equals 1, then x squared equals x. That would actually be true, because if you put in 1 for x, you'd have 1 squared, which is 1. 1 would equal 1. That's absolutely a true statement. So the original is true. Now what about the converse? It's going to read, if x squared equals x, then x equals 1. Okay, so the converse is that if x squared equals x, then x equals 1. Well, that's only partially true. If we were going to solve x squared minus x, we know this would factor into x times x minus 1. So not only would you get 1, you would also get x equals 0. It omits the solution of x equaling 0, so this is false. So the converse of this statement is actually false. Two more. Let's see. If n is greater than 5, then n is greater than 7. Alright, so the original statement is that if n is greater than 5, then n is greater than 7. All we need to disprove a statement is what's called a counterexample. If you can give even one counterexample, you can disprove the statement. So if n is greater than 5, then n is greater than 7. That's not true because 6 is greater than 5, but it's less than 7. How do we know n's not 6? So this would be a false statement. So the original is actually false. Now, what about the converse? That's going to be if n is greater than 7, then n is greater than 5. Alright, so let's see here. If n is greater than 7, then n is greater than 5. Well, that's absolutely true. Every number greater than 7 is certainly greater than 5, so the converse of this statement is actually true. So, again, it just comes down into, I mean, you don't have to do too much analyzing, but you got to read what it says. They will try to trick you sometimes. So, just got to read what it's saying here. Let's see, if AB equals 0, then A equals 0 or B equals 0. Alright, bit of a tricky one. This is a bit of a tricky one here. So, if AB equals 0, then A equals 0 or B equals 0. Well, that's basically what this is really saying here, is that if A equals 0, then B has to be something other than 0. Or if B equals 0, that A has to be something other than 0. What if they're both 0? 0 times 0 is 0, is it not? So we actually have a false statement here because it doesn't take into account that both of these could be 0. It says A equals 0 or B equals 0. It doesn't say that they both could equal 0. So that's false. Now, even if it would have said and, if A equals 0 and B equals 0, you'd still have a false statement. I'll tell you why. Because then it wouldn't take into account that A and B could equal other values. So this statement couldn't win from the start. It was false from the start. Now, what about its converse? If A equals 0 or B equals 0, then AB equals 0. So here's the converse. If A equals 0 or B equals 0, then AB equals 0. Well, that's true. If you take 0 times anything, you'll get 0. That's absolutely true. That's saying if one of these is equal to 0, then the product equals 0. In this case, that's absolutely true. So the original is false, the converse is actually true. So again, really analyzing the problem. You don't want to overanalyze the problem, but you want to figure out what it's asking you. So that's it for if-then statements and converses and biconditionals, though we will see biconditionals a lot, especially as we get further into proofs and some more of our postulates and theorems. Next lesson, we're going to review some properties from algebra and how they're going to relate to geometry. We'll even just start with some algebra proofs, then we'll do our first few geometry proofs. So I hope everyone has a good night. Take care.